we have heat transfer. This is another topic in physics. Now, in our discussion of heat transfer, we will focus only the basic concepts of heat, the laws of thermodynamics, and the modes of heat transfer. First, we have to define what is heat. It is the total kinetic energy of molecules, and if we speak of kinetic, it is moving. And heat flows from hot to cold until the heat is balanced, which we call it equilibrium. Heat is measured in calories, joules, BTU. So take note of this word BTU. We call it BTU, which stands for British Thermal Unit. Calorie is the amount of heat used to raise the temperature of 1 gram of water 1 degree Celsius. Now, what is the difference between heat and temperature? Notice, heat is the total kinetic energy available, and then the temperature is the relative measure of the speed of the particles. Now, what happens when a substance is heated? Of course, the speed of the particles increases, which causes the space between the particles to increase. Now we have thermodynamics. Thermodynamics from the Greek word thermis, which means heat, and then dynamics is what the basic concepts of dynamics is moving. So in other words, for thermodynamics, heat is moving. So thermodynamics is a science of the relationship between heat, work, temperature, and energy. In broad terms, thermodynamics deals with the transfer of energy from one place to another and from one form to another. The key concept is that heat is a form of energy corresponding to a definite amount of mechanical work. So in other words, for thermodynamics, it deals with the transfer of energy from one place to another and from one form to another. So from thermo means heat, and then dynamics is moving. So there is this heat flow. Now the laws of thermodynamics comprise 4 laws. First, we have the first law of thermodynamics, or the law of conservation of energy. The change in a system's internal energy, which we designate as U, is equal to the difference between heat, we use heat as Q, added to the system from its surroundings, and work done by the system on its surroundings. Now notice this one, the first of thermodynamics, can be visualized using this example. We have here, let's say this is a piston, and if we apply, and then this piston valve, there under this valve is let's say a gas, which is represented by U sub 1, or the internal energy of a gas. If we apply heat, of course this piston will rise up. So try to look at this one, from this point up to this point. So in other words, you have here the change in internal energy represented by U sub 1 and then U sub 2. The space here for U sub 1 is small, and then this part, of course, the internal energy is increasing. And so when this valve raised up, you have here a work done on the system, which is represented by W. So when in our equation, Q, or heat, is equivalent to the change in internal energy plus work. That is the first law of thermodynamics, or the law of conservation of energy. The second law of thermodynamics is all about heat. Heat does not flow spontaneously from a colder region to a hotter region, or equivalently, heat at a given temperature cannot be converted entirely into work. Try to look at this one. This is the hot surface, and then this is the cold surface of, let's say, this is a metal. Now, heat flow from hot to cold. That is the second law of thermodynamics. Heat does not flow spontaneously from a colder region to a hotter region. The third law of thermodynamics, the entropy of a perfect crystal of an element in its most stable form tends to zero as the temperature approaches absolute zero. So if you have noticed here, as temperature decreases, the internal energy decreases. In other words, for example, this object, if I am going, this pen, if I'm going to apply heat on this part, of course, some of this portion will change its shape. So there is this what we call as internal energy change on this part, and then the temperature of course is increasing, and then when I remove the applied heat to this portion, it will go back to its original size. Thus, the entropy of a perfect crystal of an element in its most stable form tends to zero as the temperature approaches absolute zero. So that is the law of thermodynamics. Third law of thermodynamics. The fourth law, which we call it the zeroth law of thermodynamics, when two systems are each in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other. So basically, we have here the basic zeroth law. Explain that we have here when two object or systems are in thermal equilibrium, and then they are connected, exposed in the other let's say system, then the first two systems are in thermal equilibrium with each other. Okay, so in other words, these three objects are in equilibrium. When we speak of thermal, that considers, we will consider it as heat. So in other words, their temperature is the same. For example, this one, we have here, let's say, liquid, and then if you add a liquid contains a certain temperature, and then if you add an ice wherein the temperature is very low, there's a tendency that when you mix this one, their temperature is in equilibrium. The water, this liquid from higher temperature becomes lower, and then this ice from lower temperature will slightly increase its temperature, so they are in equilibrium later on. Equilibrium is equal. Now try to look at this one in our refrigerator. This is the basic concepts of, applications of thermodynamics. We have here our refrigerator, okay, and then we call this one as our evaporator coil. This one, evaporator, side view of a refrigerator. There is this evaporator coil. So, and then that is connected to the compressor, and then after it passed to the compressor, the refrigerant inside this coil is being compressed, and then it will be delivered to, using the compressor, it will pass to the condenser. We call this one is the condenser, wherein heat is released, and then after that it will go back to, it will pass to an expansion valve and then go back to these evaporator coils. Now, what happened to these evaporator coils? Example, we have here, we put some foods inside the refrigerator. This food has its own initial temperature. So say for example water, if we put water inside a refrigerator, let's say the temperature of water is, let's say, 25 degrees Celsius. Later on, the temperature of water is not let's say decreasing from 25, assuming from 25 degrees it will become, let's say, 5 degrees Celsius, almost zero. So for that difference, let's say 20 degrees difference, that is the heat coming from the water, and that heat is being absorbed to your refrigerant inside the coil. So the refrigerant inside the evaporator coil absorbs the heat from the different foods inside the refrigerator. So that refrigerant will evaporate. Okay, so after it will evaporate, of course, that gas, it will turn into gas. So it will be compressed in a compressor, and then after passing through the compressor, hot compressed gas push out to the condenser. So from the condenser, heat is being released. That is why at the back portion of your refrigerator, you feel the hotness, okay, from the condenser. So in other words, that heat is being released from your refrigerant gas. Okay, it is being released in the air. So metal coils dissipate heat into air, and then our refrigerant now from gas might turn into liquid, and then it will go back again to the evaporator coils. So there is this a cycle of your flow of the refrigerant from liquid to gas, from liquid from the evaporator, and then to gas. So that is a cycle of your refrigerant. That is why most of your food, let's say food or vegetables that is inside your refrigerator, the temperature becomes low because the heat from your food is being absorbed or released to the refrigerant. Now the modes of heat transfer. We have the word conduction, convection, and radiation. Conduction is the transfer of heat through physical contact. Convection, heat carried from one object by a fluid motion in a gas or liquid. And then radiation is the transfer of heat through electromagnetic energy. So try to look at this one. This is an example of conduction. When we heat an object here, of course, this heat will transfer from this part until this part and so on. So there is the transfer of heat through a physical contact. Heat is in contact with your, let's say, material. Now convection, heat is carried from one object by a fluid motion in a gas or liquid. So when we apply here heat, of course, this water will increase its temperature. So remember, the particles of water is moving when its temperature is increasing. So heat is carried from one object by a fluid motion in a gas or liquid. So for this case, we use liquid. And then for radiation, the transfer of heat through electromagnetic energy. So for example, this one radiation, it is radiating. So there is what we call as the electromagnetic energy. That is the modes of heat transfer. Now simply we have this one, another visualization of the modes of heat transfer. We have here this coil, heating coil. When this heats up, it will radiate heat, and then this radiation through electromagnetic wave transfer to your pan, and then assuming this has a liquid inside your pan, so there is this process of modes of heat transfer. We call it as convection. We have this one, transfer of heat in a fluid. So that is convection. And then when the transfer of heat is through the metal in contact, so that is conduction. Conduction on a microscopic scale, it occurs as rapidly moving or vibrating atoms and molecules interact with neighboring particles, transferring some of their kinetic energy. So in other words, heat is transferred through kinetic energy. Conduction is most significant in solids, unless though in liquid and gases. So if we talk about liquids and gases, that's more on convection. So conduction is most significant in solids due to the space between molecules. Take note, in solids, the molecules are compact, while in liquids and gas, well, the molecule is, let's say, separated from each other or not compact. The rate of heat transfer by conduction is dependent on the temperature difference, the size of the area in contact, the thickness of the material, and the thermal properties of the materials in contact. We have here the key terms in conduction. The word thermal conductivity. It is the measure of a material's ability to conduct heat. Now try to examine yourself if you are in a room. Metal has high thermal conductivity than wood, and when placed in the same room, the piece of metal feels much colder than the piece of wood. So if you observe inside the room, if you touch, let's say, a piece of wood and a piece of metal, you will experience that the metal is colder than the wood. So that is because of the high thermal conductivity of the metal. Now, conduction rate equation. So this is how we compute the heat or the rate of heat transfer by conduction. We apply the Fourier's law, wherein Q, this represents our Q, or Q sub X represents our rate of heat transfer, that is equivalent to negative Ka delta T over dx, dt or dx over dx. For if we talk about dt, that is the change in temperature. So for example, we have here this one, okay, for example, we have here a metal, and then this area is the temperature is high. So when temperature is high from this area, of course it will conduct energy to this, say for example this is a metal. At this point, the temperature is low compared to this one. So if you are inside the room, the temperature is low when compared to outside the room. That depends on the situation. So for this case, T sub 1, this point, and then T sub 2. And then of course, you have here the thickness, that is your D sub X. So take note, in our case, your T sub 1 here, T sub 1 is greater than T sub 2 for this case. Okay. So again, Q equals negative K A delta T over delta X. Now, why is it that this one is negative? This is negative because heat is being transferred from higher temperature to a lower temperature. Or in other words, heat is being absorbed. So that is why we have here negative. Negative stands for absorption of heat. So our Q here is the rate of heat transfer, that is in terms of joules per second or watts. Equivalent of joules per second is watts, that is in metric units, and then BTU in English units. Remember, units is divided into two. We have the English and metric. So Q, our rate of heat transfer, and then K, that is the thermal conductivity, wherein the units is watts per meter per Kelvin, or in English unit we have BTU per hour per feet per degree Fahrenheit. And then the area, we have here A, that is the surface area. If we speak of the surface area, we have this one, the surface area for this case. This is a rectangle. So that is square meter or square feet. And then dt or delta T is the temperature difference. That is T sub 1 minus T sub 2, wherein the unit is in terms of Kelvin or degrees Fahrenheit. And then dx is the thickness in terms of meter. So this is now the thickness. Now we have here an example of solving heat by means of conduction. Determine the rate of heat transfer by conduction per unit area by means of conduction for a furnace wall made of fire clay. So for example, this is our furnace wall. The thermal conductivity of the furnace wall clay is 0.3 watts per meter per Kelvin. The furnace wall temperature can be taken to be same as furnace operating temperature, which is 650 degrees C, and temperature of the outer wall of the furnace, which is 150 degrees C. Okay, so our basic formula equals Q equals negative Ka delta T over dx, or negative Ka T sub 1 minus T sub 2. We have here our T sub 1, and then we have here T sub 2 over dx. So our T sub 1, we convert this one into an absolute value from degrees Celsius to 650 degrees C plus 270, that is equivalent to 923 Kelvin. So this is one way of converting your temperature from degrees Celsius to Kelvin. So we add 273, and then T sub 2, 150 degrees C plus 273, that is equivalent to 423 Kelvin. And then we also check our dx, that is the thickness given is 6 inches. So 6 inches, when we convert this one to meter, so 1 foot is equivalent to 12 inches. We will multiply this one, so we will cancel inches. So what remains here is feet, and then 1 meter is equivalent to 3.28 feet. This is the conversion of meter to feet. So we will cancel feet, so what remains here is meter. So when we multiply 6 times 1 over 12 times 1 over 3.28, that is equivalent to 0.1524 meter. That is our thickness dx. So that when we solve the rate of heat transfer by conduction per unit area, so that is Q over A. So we will multiply the value of K, and then dt, we have this one, the change in temperature, over dx. So that is equivalent to, we will cancel Kelvin. So what remains here is, this is supposed to be watt per square meter, because we have here meter, so square meter. So our final answer is 984.25 watts per square meter. Another mode of heat transfer is convection. Convection is driven by the large-scale flow of matter in fluids. Solids cannot transport heat through convection. Natural convection is driven by buoyant force. Hot air rises because density decreases as temperature increases. This principle applies equally with any fluid. That is why if you are in your room, at the top portion of your room, the temperature is hotter compared to the lower part of your room. Convection can transport heat much more efficiently than conduction. Air is a poor conductor and a good insulator if the space is small enough to prevent convection. Now, convection rate equation, we apply the Newton's law of cooling, wherein the formula is Q equals H times A times the change in temperature. So we use the Newton's law of cooling, wherein Q here is the rate of heat transfer, again in joules per second or watts, and in English unit that is BTU, and then H is the heat transfer coefficient, which is watts per square meter per Kelvin, and then the area is the A, surface area, is square meter in metric units, and in English unit we have square feet, and then dT, or the change in temperature, or this is the temperature difference, which is expressed in terms of Kelvin or degrees Fahrenheit. That is the formula for convection rate equation. We apply Newton's law of cooling. Now, convection has two types. We have the natural convection and the forced convection. When convection takes place due to buoyant force, as there is a difference in densities because of the difference in temperatures, we call it as a natural convection. And when external forces, external sources such as fans and pumps are used for creating induced convection, we call it as forced convection. So try to look at this one. This is hot egg. Okay, so if this is hot egg, we are going to bring the temperature of egg in a lower temperature. So we will just put it in the, let's say, environment and make remain it and just observe it, let it cooled. So we use air for its cooling, natural convection. In a forced convection, we apply here, let's say, fan. We put fan so that the temperature of this egg will lower as fast as it could because of the fan being applied. So this is what we call forced convection. Another mode of heat transfer is radiation. The energy of electromagnetic radiation depends on the wavelength or color and varies over a wide range. A smaller wavelength or higher frequency corresponds to a higher energy. All objects emit and absorb electromagnetic energy. The color of an object is related to emissivity, or its efficiency of radiating away energy. So we call it emissivity. That is the efficiency of radiating away energy. Black is the most effective, while white is the least effective, because E equals 1 and E equals 0. E here is emissivity. For black, its emissivity is equivalent to 1. So black is the most effective, while white is the least effective, which is equivalent to, its emissivity is equivalent to 0. That is why when you are wearing black shirt, you can feel the heat if you are wearing a black heat, because black absorbs more heat when compared to white, let's say white shirt. An ideal radiator, often called a black body, is the same color as an ideal absorber and captures all the radiation that falls on it. So we have this term black body. Okay, black body, that is the same color as an ideal absorber and captures all the radiation that falls on it. So black body example is your black shirt, black stone. So if you are wearing black, any black let's say shirt, again you can feel the hotness because black absorbs heat more compared to other color of shirt. Now absorptivity, this is absorption, the degree to which something absorbs energy, a liquid or another substance. For an arbitrary body emitting and absorbing thermal radiation in thermodynamic equilibrium, the emissivity is equal to the absorptivity. In other words, if you have here thermal equilibrium, okay, when the temperature is unequal, so we call it thermal equilibrium, then the emissivity is equal to absorptivity. In radiation, we have here, in computing the heat transfer for radiation, we have the formula Q is equal to this symbol, I think this is omega, times A, and then T sub 4, T sub 1 raised to 4 minus T sub 2 raised to 4. So Q is the rate of heat transfer in joule per second or watts. In English unit, we have BTU. And then this one is the Stefan Boltzmann constant, which is equivalent to 5.6703744419 times 10 to the negative 8 watts per square meter per Kelvin to the fourth. A is the surface area, that is in terms of square meter and square feet, and then T sub 1 raised to 4 minus T sub 2 raised to 4, these are the temperature difference. So our unit here is supposed to be Kelvin or degrees Fahrenheit, because that is temperature, and then that is raised to 4. This is supposed to be raised to 4, but in terms of temperature, that is in Kelvin. But T raised to 4 is equivalent to K raised to 4. So this is the formula. So that ends our discussion.